This paper is entitled, Fast Kriging-based Error Evaluation for Approximate Computing Systems. The authors are Justine Bonnot, Daniel Menard and Carol Desnos. The authors are from INSA Rennes Engineers School and the IETR Laboratory. This work has been achieved in the context of the ANR project artifact. The approximate computing paradigm is known to be efficient to reduce the implementation cost, and especially the energy consumption. To obtain a low-power system, by exploiting approximate computing, the design space must be explored to find the best configuration. This design space exploration can be modeled as an optimization process as depicted in this equation. The implementation cost is minimized as long as the quality constraint is fulfilled. The term C represents the implementation cost. The term lambda represents the quality or the accuracy metric, and lambda min is the quality or the accuracy constraint. The variable of this optimization process is the NV length vector E, which contains the different approximation sources. This design space exploration is a combinatorial optimization problem, and we have to explore a huge design space. Indeed, we have numerous sources of approximation that can be considered, and for each source different configurations have to be tested. One of the most critical part is the evaluation of the quality or the numerical accuracy. We need efficient techniques to evaluate these metrics. These techniques must be fast, to limit the optimization time, and they must be accurate to take the right decision in the optimization process. Two types of approaches can be considered: analytical or simulation-based techniques. Now, we will consider the case of techniques based on simulation to evaluate the quality or accuracy metric. The optimization time do the process for evaluating the quality or the accuracy is depicted in the following equation. The term n lambda represents the number of times that the metric is evaluated. The term ns represents the number of samples or the number of inputs that are required for one evaluation of the metric. The term ts represents the time to evaluate on sample or one input. The reduction of the evaluation time can be achieved by optimizing these three terms. Let's consider the time to evaluate one sample. To simulate the effect of the approximate computing technique, a piece of code is used to replace the original operation or processing, for each source of approximation. This increases significantly the simulation time. For example, in the case of approximate operators, the simulation time can be increased by 3 orders of magnitude compared to a native floating point operation. So, it is important to optimize the emulation code in order to reduce its overhead. In the case of approximation due to finite precision, efficient C++ classes have been provided for custom precision data type, like in System C. Now, let's consider the number of samples required for one evaluation of the metric. Most of the time an arbitrary number of samples are used for the simulation. This number must be high enough to ensure a good estimation. Nevertheless, this number can be adapted and adjusted according to the required precision. Inferential statistic can be used to control this number of samples ns. Now, let's consider n lambda, the number of times that the metric is evaluated, or more precisely, the number of times that the metric is evaluated by simulation. This number can be decreased by replacing the value obtained by simulation by a value obtained by interpolation. This is the goal of this contribution. We have developed an interpolation technique based on the Kriging-statistical approach. Kriging carry out a stochastic spatial interpolation. The technique estimates the quality metric lambda for a given configuration vector EI. This estimation is obtained from the already known values of the neighbors EK with a linear relation as depicted in this equation. Kriging technique provides an unbiased linear estimation with minimal variance. The hypothesis to exploit kriging is that the surface to interpolate must be continuous. So, how the weights μ k depicted in the linear estimation are computed. These weights are obtained from the semivariogram. The semivariogram models the spatial autocorrelation of the measured sample points. Once each pair of locations is plotted, a model is fit through them. Let n d the set containing the couple of point jk, for which the distance is lower or equal to d. The semivariogram analyze the correlation on all the couple of point jk of the set nd. We have seen that with the Kriging approach, it is possible to estimate the quality metric from its neighbors. Now, we have to verify if this kind of technique is interesting in the context of optimization process during design space exploration. In the DSE we have to explore a huge space. But, at the end, few configurations are tested. So we have to answer to the question, is the trajectory of tested configurations allows exploiting interpolation with Kriging? To illustrate that we consider the case of word length optimization, we use the min plus 1 bit algorithm in the case of two variables. This optimization algorithm is a greedy search and middle ascent optimization algorithm. On the figure, you can see the different points that are evaluated during the optimization process. Now, I will present you the results of the experimentations. The fixed point refinement process is considered as the design space exploration with approximate computing. The variables of the optimization process are the data word length. The accuracy metric is the noise power at the output of the application. The quality of the estimation obtained with the Kriging approach is expressed as an equivalent difference in number of bits. The error epsilon gives the difference in number of bits between the estimated value and the real value. The results obtained for the fixed point refinement are presented in the following table. NV is number of variables of the optimization process. D is the maximal distance between the neighbors. P is the ratio of evaluations obtained from estimation instead of simulation. The goal is to have the higher value of P and close to 100%. Mu epsilon is the mean of the estimation error epsilon. Increasing the distance allow to increase the ratio P. Indeed, when the distance is higher we have more chance to have in the neighborhood configurations that have been evaluated and that can be used in the Kriging process. What is interesting is to see that the ratio P increase when the number of variables NV of the optimization process increase. These results show that up to 90% of the points can be estimated in the case of the HEVC application. The second set of experimentation has been done on the error budgeting process. In this process, the optimization variables are the error power of each internal source. The application is decomposed into blocks and an error source is associated with each block output. The goal is to find the maximal error power tolerated at the output of each block. The considered application is a convolutional neural network. A source noise is associated to the output of each layer. The quality metric is the good classification rate. This is the ratio of cases when the classification is different between the initial one without approximation and the one with approximation. The quality of estimation is expressed as a relative difference between the real and the estimated value. The results obtained for the error budgeting process are presented in the following table. NV is number of variables of the optimization process. D is the maximal distance between the neighbors. P is the ratio of evaluations obtained from estimation instead of simulation. Mu epsilon is the mean of the estimation error epsilon. Like for previous experiments, increasing the distance allowed to increase the ratio P but increase the estimation error epsilon. These results show that up to 90% of the points can be estimated in the case of a distance d equal to 3. It means that the evaluation time can be divided by a factor of 10. To conclude, in this paper, we have proposed an interpolation method based on Kriging. This approach allows reducing significantly the number of configuration to simulate. The best results in terms of accuracy are obtained with small value of the distance d. For the future works, the method will be extended to estimate a confidence interval instead of a value. Thanks for your attention.